Satellites are an essential modern communication tool. As well as serious science and, dare I say it, frivolous things like satellite television, we use technology in orbit for monitoring weather, navigation, and for global communication. Nation-states rely on space technology such as satellites for secure communications and for intelligence gathering. But satellites are exposed to a number of risks, both natural, such as space weather effects, and man-made. Radiation from nuclear explosions could permanently alter computer systems on board. Another, altogether more nefarious threat is that of cyber criminals, who could take control of the satellite itself or intercept the messages that it sends. Diplomatic and military communications rely on being protected through encryption, but if this system fails, it can put lives at risk. To keep messages safe, essential devices are equipped with a key known as a crypto, which is hard-coded into a computer chip and matched to a key down here on the ground. This key then allows you to understand the encryption. I'm Ben Valsler from The Naked Scientists, and to find out more about the importance of keeping our satellites secure, I visited the Defence Science and Technology Laboratory, or DSTL, to meet physicist Harj Jolly.
We are critically reliant on satellite communications to provide us with our long-haul communications to far parts of the world where there isn't a telephone infrastructure. So it's particularly important for people like the MOD, where we send our ships and our young people to far-flung parts of the world. They need to be able to talk to us for command and control. You can't do that without satellites. The other thing, of course, is the global positioning system. We haven't had a big tanker fall on the rocks in Cornwall or something for quite a while, and it's mainly, I think, because we have better communication systems and we have better navigation systems through GPS. The other thing, of course, is something we call in the military area ISTAR, Intelligence, Surveillance, Target Acquisition and Reconnaissance, spy satellites. And that gives us an indication of a potential threat or a risk to our interests around the world.
A lot of what you've mentioned so far is in the commercial realms. You have communications, GPS and so on. Can the military piggyback on that, or do you need your own separate set of satellites and separate set of technology?
That's a good question. We actually need both. We need to piggyback because we haven't got the capacity, but we do need a hardened backbone, both for redundancy and for when things really go wrong. We need to be sure that we can rely on this stuff. And to that end, the UK has a hardened, secure, resilient satellite communication system called Skynet 5. GPS is an interesting one. It's a military system in itself. We use that just like people all over this country do to drive around their cars and that. But of course, we get access to the military signal, which is a lot more resilient and tough than the commercially available system that's used in our cars.
You've mentioned resilience, and you said that we have a hardened backbone. What do we need to be resilient against?
The main threats are things like cyber criminals. If they could get into a military communication satellite or a military system, they'd be crowing about it. Maybe rightly so, because we do try to make sure these things are quite tough and hard. There's, of course, there's the worry of a nuclear conflagration, whether not against us so much these days, but us being affected by someone else's shot across the bows or those sort of things. So these sort of systems are still quite strongly hardened to some extent to those sort of effects. I don't want to use the word fallout, but that's really what it is, fallout from someone else's problems. The other problem, again, is space weather, which is something that we can't really predict very well at the moment, but where I think our friends in the Met Office and STFC are looking into all those sort of things. We're lucky in the MOD in that the nuclear hardening that we have applied in the past, it's a Cold War legacy really, to our systems, means that we're quite hard to the effects of space weather, which are very similar to some aspects of a nuclear weapon detonation. We're not complacent, but we keep an eye on what the threats are and the risks those threats coming to pass are.
So with a nuclear blast, it's not the explosion that you're worried about, but the radiation, the electromagnetic radiation that comes off. How can you test something to determine that it's been hardened without putting it next to or above a nuclear blast?
In the old days, in the 1960s, the US and the Soviet Union exploded quite a lot of nuclear weapons in high altitude, above about 30, 40 kilometres if you explode a weapon above that sort of area, you get something called a HANE, a high altitude nuclear event. And what that basically does is that it doesn't give you much blast, but there's not much atmosphere up there, about 30 kilometres. You're only talking about 1 millibar. But what you will get is lots of radiation maybe going up to produce artificial Van Allen belts, which will destroy, damage your satellites. You'll get an EMP on the ground, electromagnetic pulse, through the generation of Compton electrons in the upper atmosphere. These electrons are swept up by the Earth's magnetic field, and bam, you get lots of radio frequency all over the place within line of sight of the weapon. These can knock out power grids, telecommunications, all those sort of things. Any long conductors will be affected. That's very similar, the effect is very similar to a geomagnetically induced current from a solar flare, which perturbs our magnetic field, and as it bounces back, you get this induced current in long conductors on the ground. So there are similarities in the effect, the origins obviously being different. And you can test for those sort of things. There are simulators which were built for Cold War applications, and they still exist. They exist at Aldermaston, they exist in America, they exist in France. We're now using these swords as ploughshares more. So we're looking at space weather effects with these sort of things as well, and that will become more the case.
Space weather has been a hot topic for the astronomical community worldwide, and we are slowly developing an ability to predict these events. You've mentioned that you do use the commercial satellites as well, which presumably aren't as hardened as your own, as you said, reinforced backbone. So are we looking at using predictions to prevent damage occurring to your second layer, this commercial system?
Yes, we are. The commercial satellites are quite hard. They're hardened to what they have considered to be bad solar events. But of course, there could be a kind of black swan event, which is much, much worse than anyone has ever predicted. After all, we've only been in space for a relatively short time, and we haven't been so dependent or susceptible to these effects. So if you get one of these events every 100 years, where we maybe do one, for example. So we don't really know. What we're doing is we're making sure if we know anything that's going to happen, if we have any prediction, we can tell our suppliers that there may be something up, something might happen. As soon as we know, they will know as well.
Going back to what you were saying about cyber security, that must be a constant battle to keep up with, or occasionally to catch up with hackers or cyber miscreants of one sort or another. How does that process actually happen?
There's a number of different areas. I mean, of course, government departments are the subject of cyber attacks all the time. A lot of these are just barrage type attacks, people trying to send lots of emails to a site, all that sort of stuff, which we can, of course, handle. The stuff that's a little bit more difficult, and we do worry about, is nation states. Of course, the capabilities and resources a nation can put to bear on cracking encryption codes is way different from a spotty teenager in his mum's 3-bedroom semi in Hounslow. That is a problem, but we do work with our friends at GCHQ in the Foreign Office to give us an idea of what the threats will be like, even based on Moore's law, where computing processing power, memory doubles every 18 months or so. So little trends like that are used to work out what the level of crypto threat will be to our encrypted systems, which include our satellites. The problem with that is we have to have quite a long view of this. The satellites, our military satellites, have a lifetime in the order of 15 years. The system itself will have a lifetime in the order of 20-something years. So the cryptos produced on the ground will have to do their job for 20-odd years. So we have to not just deal with the threat today, but deal with the threat that will be around in 20 years for our satellites, because we can't go up and change the cryptos.
So you obviously need to have devised ways to future-proof the satellites.
The satellites use something called symmetric encryption, which is basically they have a chip on their satellite and we have encryption on the ground. Basically what happens is that you can't change the chip. If you could, maybe a space weather event could change it for you, which is not what you want. So these things are quite carefully engineered. The software on the ground is okay. We can keep updating the ground stations and all that sort of stuff. But the space elements are quite tough. It's basically a hardware crypto. You do have some issues of key management, but you put those up into memory, and you must ensure that memory is not susceptible to single event effects where radiation from the sun can change memory elements. They can change them from reading ones to zeros or vice versa. So you really don't want that in your crypto if you've got a 200, 300 million pound satellite where you can't, won't let you talk to it. So that's a big challenge, and it always has been.
And can you learn from the direction that the academic community is moving in? Presumably you do your own research as well, but when relying on academia, you've got the whole world's research that you could bring together. There are all sorts of interesting new developments in quantum encryption, in new types of computing. All of these must feed into your future profile.
That's very true. In fact, a lot of these technologies you mentioned, quantum computing, are potentially threats. If someone could build a quantum computer, they could probably crack our cryptos quite quickly, which would mean that all the satellites we have up there would be susceptible to nefarious hackers. So we do keep an eye on all these things. We do work quite closely with universities and also industry, but also we work quite closely with this STFC, the Science Council's UK Space Agency. We have suitably cleared academics throughout the country, and they come and review our work independently. For example, we wouldn't be doing our job if we didn't exploit the huge amount of good science and technology research that is done outside in what you might call the real world, as opposed to our military domain.
Harj Jolly from the Defence Science and Technology Laboratory. I'm Ben Valsler, and for more science news, interviews and podcasts on a very wide range of science topics, join us online at thenakedscientists.com.